So now we can run that model. If you remember in class, Ebua said that we have to always be careful when we run categorical variables, that it's easy for R to, if you just put a categorical variable in the model, R will not tell you that it's a categorical variable unless you say it to R that, oh, this variable that we're doing is a categorical variable. Okay? So if you didn't tell R that it's a categorical variable, I would assume that it's a numeric variable. So if you run it like that, it will interpret it as if it were a continuous variable with 4 levels. And you get this estimate, which is wrong. Okay? The correct way to do it, one correct way to do it, is to tell R that I want you to run this variable as a factor. And if you remember, we said a factor in R refers to a categorical variable. So now R will know that the variable that you're looking at is a categorical variable. And if you run that, this is what you will get. What's the difference between this estimate, this regression, and the first one? Let me zoom out so you can see both at the same time. So now it's small, but if you move closer to your screen. So this is the one that we did first. Okay. And this is the one that we are doing now. Anyone wants to tell us what they think of the two that's different? If you just pay attention to this column and this column. Anyone? Do you see that here you have one line, but here you have 3 lines?
Yeah.
Right. So you have 3 lines because R is now correctly realizing that this is a categorical variable. Okay? Because R is now correctly saying that this is a categorical variable. Let me zoom back in. You can see it correctly. Okay. Now, let's attempt to interpret. Okay, let's attempt to interpret. Anyone want to, let's start with Gloria. I think you answered the first question. So I want you to give this one a shot. What does this estimate mean? If you remember, we said that one house category, house category 1 is when the variable is, or you know what, let's do this differently. Let's do this differently so that it's less complicated for you to interpret. Okay. So I'll create another variable and call it house category X. And I will actually say less than 40 volts. See someone is writing on their screen. We can see what you're doing. It's Gloria. I think it's going to get on everybody's screen. Unfortunately. Oh. Yeah. Oh, let's say okay. Just for simplicity. 1, 2, 3, and then here we will say 31. Okay. So let's run this. All right, can you try to interpret this now? I think this is easier. So Gloria, can you go first?
Okay. Let me give it a try.
Yeah.
So if you look at the data, look at the results that we got, you will see that the categorical variables of 41 to 60 and 61 to 80
No,
are
interpret one first. Just interpret one. Interpret
yeah, I'm
41
just trying
60
to
alone.
say that. Okay, for the first one.
Yeah.
For the first one, it means it's a positive, it has a linear positive relationship.
Yeah.
And then if you look at the p-value, the p-value is quite higher than 0.05,
Yeah.
which means there's no relationship.
No relationship. Very good.
Yeah, there's no relationship. So when you compare it to the intercept, at the intercept, it means that for all the groups that are between 41 to 60, it means for every hour between that 41 to 60, there's a 0.3472 increase
in the mental health score. That is
in the mental
excellent.
health.
Yes, that is excellent. So basically what he said is that the estimate of 0.34 or 0.35, whatever, is the increase in the mental health score that you will have if you work 40 to 60 hours compared to the intercept. And what's the intercept? Anybody else want to tell us what does the intercept represent here? Which group is the intercept? Dr. Cheloka, do you want to tell us? I'm just going down this on my screen. Let me try. Who is the intercept? Mahmoud, we're going to call you next. Mahmoud, do you want to try? Maimuna, do you want to try? What is the intercept here?
I think the intercept is 23.9231.
Yes, but what does it represent? Very good, yes. What does it represent? Which group is the intercept?
The intercept stands for the 3 group.
Not quite. So remember here we have 4. If you remember this analysis, there's 4 groups, right? Let me go back and show you. Stay unmuted. So here we have group 1, right? Less than 40, 41 to 60, 60 to 80, and 81 plus hours, right? This group is less than or equal to 40. But if you look at the output, do you see less than or equal to 40?
No.
So that group is
41 to 60.
Yeah. So this less than or equal to 40, that is the intercept. So the intercept, okay, the intercept is also known as a reference group. It is the estimate, it's the group for which all the other categories are set to 0. Okay, that means that this is 0, this is 0, this is 0. And in this case, that is the 41 to less than or equal to 40 group. Is this clear to everybody? The reason why it's important thank you. The reason why it's important to emphasize on the intercept, which is also the reference, is because we're going to compare. If you remember when Gloria explained this beta estimate, it said that compared to the group, the intercept group, right, which is the less than 40 group, the change in the mental health score is 0.35 for those who work 41 to 60 hours. Okay, so who is going to explain to us what 0.59 represents? Maimuna, do you want to give it a shot? If you remember, we said that 0.34 is the change for those in 41 to 60 group. So what is the
similarly, 0.59 is a change too for the people in this category.
Yes, compared to what?
Compared to 23, the reference group.
Compared to the reference group. Very good. Okay. It is always important to remember what it is compared to. Okay. Always important to remember what it's compared to. And the same thing for this group compared to the reference group. Okay, excellent. You guys are doing very good. So the other thing that we're going to point out is that for categorical variables, we have 4 groups, right? But when our model did, it presented 3 groups with the intersect. I would say the intersect is the reference group. So sometimes we can model categorical variables as indicator variables, dummy variables, okay? And so this essentially we create many variables, outstep 1, outstep 2, which are essentially dichotomous variables where you're either 0 or you're 1. Okay, this is 0. You're either 0 or you're 1. So if you have 4 variables like that, 1, 2, 3, 4, which correspond to the groups that we saw earlier. If you run this model here, okay, Glory, do you think you can clean these lines off your screen? If you run this model, you will realize that it's the same model that we just looked at for the categorical variables, right?
Yeah.
Everyone agree? Yes, exactly. So the difference is that now we've gone and first of all created four different variables. The thing to remember here is that the variable that you leave out is the intercept. So here we have house cat 2, 3, 4. We left out 1. But what if we had left out house cat 1? Okay, that means in this case, now we are comparing all the other variables to the 2 variables, to those in the house category, in the hours category, 41 to 60. So you see how the results suddenly change. Before we didn't have anything that was significant, but now we have this is significant. Okay? The reason why it's important to understand this is that the reference that you choose, it changes the interpretation of your results. It also changes the magnitude of your results. So it's important to bear in mind what exactly you're doing. This becomes even more important when you're modeling things like obesity, right? So if you're modeling obesity, you might have 4 categories where you have underweight, normal weight, overweight, and obese. Now, if you make underweight your reference category, the results you will get is different from if you made normal weight the reference category, right? And more often than not, we want to see normal weight as a reference category because that's what the vast majority of people are. But if you just did it like 1, 2, 3, 4, the way we did it initially, you will be comparing everybody to underweight. You know, underweight itself is a pathological state. Okay, so we want to compare everybody to a normal state, so that gives us a more meaningful that way. Is this point clear? Because now I'm moving to linear regression. Okay, to multiple linear regression. So in the context of multiple linear regression, it's essentially the same thing that we just did, but we can include more than one predictor variable or covariance. Okay, a number of reasons why we might want to do that is to improve prediction or to adjust for confounding. Okay, and So this is the same variable we just saw, the same model we just saw. But somebody might say, you know, what if we adjust for gender? Maybe all the maybe the relationship that we saw earlier is because females work many more hours than males, or maybe females work fewer hours than males. And so you can't just compare the hours worked to their mental score if there's a relationship between the female and the hours worked and the female and the mental health score, which makes female a confounder. And somebody might say, oh, maybe all the relationship they're seeing is because of the confound. And you know what? Let's make this one because there is no relationship. Okay? So you decide, well, let's adjust for female for gender. So when you adjust for gender, you remember what we saw earlier? Remember what we saw earlier when we made this the reference? This was the value of the beta estimate that we have, minus 2.04. But when you adjust for gender, this becomes minus 2.05. So it changes very slightly. And the beta estimate itself for gender is not statistically significant. Okay? So that's what you do. You just add it to the model, you know, and then you move forward. Okay? The more interesting question is, how do you decide when to add female to the model? Or how do you decide when to add specialty to the model? How do you decide which other variable to add to the model? And that's often, if you think that it's a confounder, and I explained that a confounder is a variable that is related to both the predictor and to the response variable. It has a relationship with them. So that means that it could also explain the relationship that you see here. It might be that all the effect of mental health score that you're having through hours work is actually because of gender. Somebody might say, oh, it's gender that's really driving the relationship, okay? So you adjust for it. But the other thing that I wanted to point out to you is the R squared. Look at this R squared, okay? So if you look at the R squared in the first variable, it was 0.0794. This one, let's look at this one, 0.0928, okay? But when you add a variable to it, this increases slightly, okay? Because every time you add a new variable, the R squared increases. But if you want to do a multiple linear regression, then you should always pay attention to the adjusted R squared. If you have more than one variable in the model, use the adjusted R squared, because the adjusted R squared, it accounts for the number of variables that you have in the model. Okay? So that's the R squared thing. We have 10 more minutes. And I want to just quickly talk about interaction terms. Okay? So you can go through the other examples that I just did, but I want to quickly talk about interaction terms. So interaction terms are essentially a way for us to look at how the results differ, okay? How the results differ in how the relationship differs as a function of a third variable. Okay? As a function of a third variable. All right. So if you look at this model where you have hours, category, and the number of children, the category as well, and the age. If you run this model, okay, I didn't create that. So there were skip lines. Let me create that. So if you create this variable, and Now, if you run this model, so look at this model carefully. We have 3 variables, but they're all categorical, and each of them have like their own. So the intercept here, let me explain this carefully. This intercept refers to when you set all of this to their reference categories. You can imagine that ours category has its own reference category. This ours cat has its own reference. The reference is less than or equal to 40. Okay? This variable has its own reference. And then this variable has its own reference. But the people who belong to the reference for all 3 variables, that's the intercept. The intercept refers to the people who belong to the reference for all 3. It's a union of the intercept for this, this, and that. And you set all of this to the reference. Okay? But we can also, rather than just add this to the variable like we did, we can run the model with an interaction time. If somebody says the effect of the number of children is different depending on the age of the woman or of the resident of the woman. So if you run that, okay, you will, okay, that's something good. Yeah, that's really okay. So if you run this model, the results that you will see, so you see all of a sudden you have all this very seemingly large model. Okay, if you avoid, don't just ignore the NAs for now, but look at this. Because basically what it's doing now is that it's doing multiple pairwise groups and creating like, it's essentially multiplying each group by each group. So if you take it to a 2x2 setting, where if you were looking at a model of female versus male and adult versus child, right? In that kind of setting, and that's simplifying it to make it easy to understand. In the initial model, we would have had one beta estimate for adult versus child, one beta estimate for female versus male. But in this case, with an interaction term, now you will have the beta estimate for adult versus child, the beta estimate for female versus male, but you would also have one beta estimate for adults that are, that an interaction term for gender and age, and if you've done it as a factor variable, then you present all the different levels. So let's attempt to interpret one of these interaction terms. Okay. But before we do that, let's ground ourselves in this model. Okay. This is the intercept, and it's the same intercept that we saw earlier, 24 point something. This exponent is just saying move the decimal place one way, multiplied by 10, something like that. Okay. So this is the intercept, which is when everything else is 0. If the person falls in the hours, in the second hours category, this is the change in their mental health score compared to the intercept group is minus 11, is minus 1.1. Okay. And is minus 11. Okay. And the change in, if they were in the 3 category, it will be minus 22.5. All right. But if they had a child, then this will be much larger. It will be much smaller because it's a negative. Okay. But if you were looking at, I think we need to find, let me find a simpler example. And then I will write out the example in clearer terms, and hopefully that will be easier to explain. But the idea really is that for people who have one child and who are 30 to 34 years old, they would have this beta estimate on top of, that'll be the change in the beta estimate that they have on top of their age category estimate and the number of children that they have. You know, that's the way that you'll be able to guess their mental health score. But in this case, right, all of these interaction terms are not significant, as you can see from the p-values. So we often wouldn't bother about the interaction terms that are not significant. We have 5 minutes. I'll take questions, and I think that we'll have to go through these interaction times again in a way that will be easier to understand. But I'll take any questions at this point.
Yeah.
Okay. Yeah, go ahead.
Yeah, so basically, I was going to call your attention back to the confounders.
Okay.
So when we talk about confounders, you said something that has a correlation.
Yeah.
That correlates with the other one. So basically, it's like when you say this particular variable will have a more suppressing power over every other variable. Is that what you tend to mean?
Kind of, yes. It's not a more suppressive power. It's just an alternative explanation.
So basically, determining a confounder might be a bit challenging because you cannot, like the case where you use a female and then you are bringing it based on obesity. You cannot completely say females are more obese. So because by the time you now use female as confounder, doesn't invariably means that obesity has a correlation with feminine.
That's basically what it means. So it's not a correlation per se, it is a relationship. And remember we said correlation is linear, it's continuous setting. Yeah, so it's a relationship. So I'm just going to share this slide very quickly. So in March, I think we taught a class, EP 101, where we explained some of these concepts. And we can talk about making available the videos to you guys after if you're interested. But one of the concepts that we explained in that class was confounding. Can you see my screen?
Yeah, I can see.
Okay. So basically, for a variable to be a confounder, it has to be associated with the exposure or related with the exposure and related with the outcome. And that's what I explained, that it's related to both the predictor and the response, right? But also it should not be in the causal pathway between the exposure and the outcome. That means that the exposure did not cause it to lead to the outcome. Now, but how do we know that something is a confounder? It's often from our understanding of the subject matter. Okay, so if you're a nutritionist, for instance, and you see a lot more, females that are obese, for example, right? So if somebody tells you that maybe obesity is more related to mental health, for instance, let's just say maybe depression, okay? Now, as a health worker, you think that there's, and I'm just guessing, I'm not basing this on any subject matter, I'm just saying that, say for instance, you think that females are more likely to be obese, but also females are more likely to have depression. Okay, so if somebody tells you that obesity is associated with depression, you might ask them, are they sure it's not because of the gender? You might ask them, are there more females in your data set? right? So you ask them, oh, can you check females as well? Because if maybe there's a relationship with females with gender in your data set, then maybe that's what's explaining what you're finding. So gender becomes an alternative explanation for the phenomenon, and that's a confounder. Okay? It's basically something else that somebody can. Go ahead.
Okay, so now, if we call female in this instance, let's say, for instance, we call female a confounder.
Yeah.
And now, do we still want to go ahead and probably look across the male and see if there is actually, it is a confounder?
We can, yeah. That's one of the things that we can do to actually look at the relationship to see whether that is to see whether this is likely to be the case. And there are ways that we do it. Okay, but if you assume that it's a confounder, you can adjust for it in the regression model. And that's one of the things that we do in multiple linear regression. Okay?
So in adjusting for it, so what exactly are you trying to achieve?
In adjusting for it, excellent question. What you're trying to achieve is you're trying to remove the effect of female, of gender, from the relationship that you're truly interested in. Okay, so if you remember when in physics, we usually say that all things being equal, you know, like you will say that all other things being equal, that this is what you find. And that's the thing you're trying to achieve. You're trying to achieve a situation where, on average, between the number of hours worked and the mental health, right? Assuming assuming gender is not a factor, this is what you will find, right? So assuming that now you've held the hand of gender back and say, hey, you don't get involved in this thing. That's what you're trying to do in multiple linear regression.
Okay, now, so basically what you did is to suppress gender.
Correct, to suppress it.
So every variable you collect that is gender related is silenced.
It's sort of silenced, yes, in the model.
Okay.
Yeah.
So let's say for instance, you measured the weight of, let's say, 5 male,
yeah,
and then 5 female. And so what you're doing is you're looking at the weight without making reference to gender.
Correct. Without making reference to gender.
That's better.
It makes it more like a randomized trial. You know, in a randomized trial, yes. So you're creating a pseudo population that is more like a randomized trial.
Yeah.
Unfortunately, I have to jump off. I have another meeting to be at. I'm already 3 minutes late to it. Thank you very much.
Can we get this PPT?
You said?
Can we get this PPT?
This PowerPoint, I can send it to you, yes.
Yeah.
Okay. All right. Thank you very much.
Thank you.
All right. So if you want that PowerPoint, can you please send me an email? Send an email to Stats Clinic, and then we'll send it to you.
Okay.
So we don't have to send it to like the whole class.
Okay.
Okay. All right. Thank you very much. Thanks everyone. Enjoy the rest of the day.